Welcome to the deep dive. Today we're jumping right into something really fundamental, maybe one of the trickiest bits of physics out there.
Mm,
How matter actually behaves down at the atomic level.
that's right. We're tackling the ideas in the chapter on quantum behavior.
And it's so crucial because, classical physics is great for everyday stuff like a coffee cup or, I don't know, planets.
Works beautifully.
But the moment you try to apply it to an electron,
Mm.
it just falls apart
Yes,
completely.
completely fails. Yeah.
We've talked about light acting like waves, classically speaking, and that gets you pretty far. But matter itself, these tiny particles,
Mm.
the old rules just don't cut it.
Mm-hmm.
So this deep dive is kind of an excursion, right? See what classical physics is sort of papering over
Yeah.
when we talk about bigger things. We need this foundation.
Exactly. And we're talking about quantum mechanics, which is really just the description of matter in, well, all its details, especially when you get down to the scale of atoms. And the core strangeness, the bit that really messes with our intuition, is that these atomic things, electrons, photons, whatever, they aren't like anything we know from our direct experience.
So not tiny balls, not little waves.
Nope, not billiard balls, not clouds, not ripples in water. They're something else entirely. It defies easy labels.
Historically, this must have been incredibly confusing. I mean, light started as particles, then it was definitely waves, then it turned out to be particles again, photons.
A real back and forth.
And electrons were particles, but then they started acting like waves. So where did physics land? What are they?
Well, the answer seems to be
Yeah.
they're like neither. But here's the lucky break, maybe.
If,
The quantum behavior, this weirdness, it's actually the same for all these fundamental particles. Electrons, protons, neutrons, even photons.
so there's a universal rule underneath it all.
Yes.
Yeah.
If we can figure out the rules for one, like the electron, those same rules apply across the board. That simplifies things, thankfully.
All right, so what's our mission today? How do we get a handle on this?
We're going to walk through a specific thought experiment. It's idealized, sure, but it contains, as Feynman puts it, the only real mystery of quantum mechanics.
But a double-slit experiment.
The very same. If you can wrap your head around the paradox in this experiment, you've basically grasped the central problem, the core difficulty of quantum mechanics, something absolutely impossible to explain with classical thinking.
Okay, let's do it. But first, maybe set the stage with things we do understand classically. Let's start with, say, bullets.
Good idea. A classical particle baseline.
Right. Imagine a machine gun, just spraying bullets randomly but steadily,
Yeah.
and there's a thick wall, like armor plate, with two narrow slits in it. Let's call them hole 1 and hole 2.
Okay.
Behind the wall, we have some kind of detector, maybe a backstop, that can move around and measure how many bullets land at each spot. It measures the probability, P, of a bullet arriving there.
So what do we see with bullets? First, they arrive in identical lumps. Always a whole bullet, right? Never half a bullet.
Makes sense. Discrete packets.
And second, if you leave both holes open, the pattern you measure at the backstop, let's call it P12, is just the simple sum of the pattern you get with only hole 1 open P1 plus the pattern you get with only hole 2 open P2.
So P12 equals P1 plus P2.
Exactly. The bullets going through hole 1 don't care about hole 2 being open and vice versa. They just add up. No interference. That's the rule for classical particles.
Simple addition. Okay, baseline established. Now what about classical waves? Let's swap the machine gun for maybe a stick jiggling in a shallow tank of water.
Perfect. A wave source. Same wall, same 2 holes. But now our detector measures the wave intensity, how much energy is arriving at each point.
And what's the key difference here?
Well, first off, intensity isn't lumpy like the bullets. It's a continuous measure. It can be strong or weak or anything in between.
Right.
But the really critical thing is interference. When both holes are open, the intensity pattern I12 is not just I1 plus I2. Absolutely not.
Okay, why not? What's happening?
The waves spread out from each hole, that's diffraction. And where those spreading waves meet, they interact. If crest meets crest, they add up. You get a stronger wave, higher intensity. That's constructive interference.
A maximum.
A maximum, yes. But if a crest from one hole meets a trough from the other, they cancel each other out. You get little or no intensity there. Destructive interference. A minimum.
So you get this pattern of bright and dark stripes, essentially. Maxima and minima.
Precisely. That characteristic interference pattern.
And you mentioned earlier there's a difference in the math, too.
Briefly. Yeah. Without getting lost in the weeds, the idea is this. For waves, you don't just add the final intensities. You first add something called the amplitude. Think of it like the wave's height or its complex influence factor. You add the amplitudes from each hole first, $h plus h22, and then you square the result to get the intensity, $h plus h222.
And squaring that sum is what creates the interference terms, the cross terms that aren't in just I dollars plus I22.
Yeah. Exactly. That's where the maxima and minima mathematically come from. It's fundamentally different from just adding the intensities like we did for bullets.
Okay, I think we have the classical rules down. Particles arrive in lumps, probabilities add, waves. Continuous intensity, amplitudes add first, leading to interference.
That's the setup.
All right, now for the main event. Let's bring in the electrons. Same setup. Electron, gun-firing electrons, wall with 2 holes, and a detector behind it. What kind of detector? Maybe like a Geiger counter?
Yeah, something that clicks, like a loudspeaker connected to a detector, giving a sharp click for each electron that arrives.
Okay, so first observation, what do we hear?
We hear sharp, distinct clicks. Click, 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 click. Each click is identical. The electrons arrive one at a time in identical lumps, just like the bullets.
Okay, so particle behavior, seems like
Well,
it.
that's what observation 1 tells you. Feels like particles.
But then, observation number 2. What happens when we let this run for a while and map out where all those clicks happened? What does the overall pattern, the probability distribution look like?
And here's the kicker. The probability distribution, P12, shows the wave interference pattern, maxima and minima, just like the water waves.
Whoa, okay, wait. They arrive like particles, discrete lumps, but the pattern they form over time looks like wave interference.
Exactly. P12 is not equal to P dollars plus P22.
Doesn't make sense classically. How can that be?
That is the fundamental paradox. If they arrive in lumps, like particles, then logically, let's call it proposition A, they must go through either hole 1 or hole 2.
Seems unavoidable. It has to go through one or the other to get to the detector.
But if that were true, if proposition A holds, then the probabilities must add up, just like the bullets. P12 should equal P dollars plus P22.
But it doesn't. It shows interference.
Which means proposition A must be false. They somehow don't just go through hole 1 or hole 2 in the classical sense, and yet every single time we detect one, it arrives as a complete lump at one specific point.
It's like it knows about both holes, even if it only goes through one.
Yeah,
or something. This is weird. Feynman mentioned something even stranger. Sometimes closing one hole increases the number hitting a certain spot.
Yes. Think about a minimum in the interference pattern. Electrons actively avoid that spot when both holes are open. But if you close one hole, say hole 2, then electrons can arrive there from hole 1. So closing a path makes more electrons arrive somewhere.
How does an electron going through hole 1 know whether hole 2 is open or closed? It seems impossible.
That's the mystery right there. The only way physics has found to describe this mathematically is to borrow from wave theory. Electrons arrive like particles, yes, but the probability of arrival is calculated like wave intensity.
So not adding probabilities, but adding those amplitude things first.
Exactly. We assign a complex number, a probability amplitude, let's call it $0 dollars, to each possible path. So $0 dollars for going through hole 1, $0 dollars, $2 for hole 2. The total probability P12 is found by adding the amplitudes first, then taking the magnitude squared. P12 equals Z1 plus Z22, 2.
And that formula naturally produces the interference pattern, just like the wave formula did.
It's the only mathematical framework that works. It correctly predicts the observed pattern.
Okay, my brain hurts a little. But the obvious next question is, can we just look? Can we watch the electrons and see which hole they actually go through?
The natural instinct. Let's try to catch them in the act. Modify the experiment. Put a strong light source right behind the wall between the 2 holes. When an electron passes through, it should scatter some light, and we can see a flash near hole 1 or hole 2.
All right, so we turn on the light. Now what happens?
Okay, 2 shocking things happen. First, the observation shock. Every single time the detector clicks, signaling an electron arrived, we do see a flash. And the flash is always near hole 1 or near hole 2, never both at once.
So when we look, proposition A is true. They do go through one hole or the other. We caught them.
It seems that way. When observed, their path is definite.
Okay, so what's the second shot? We saw which hole they went through. Does the pattern on the detector change?
That's the outcome shock. The moment we turn on the light and start watching, the interference pattern, the maxima and minima, it completely vanishes.
Gone. What replaces it?
It gets replaced by the classical pattern, P12, P1 plus P22. Just 2 humps added together, exactly like the bullets.
So the very act of watching destroys the quantum interference.
Precisely. Turn the light off, the interference comes back instantly. Turn it on, it disappears. Measurement changes the outcome, fundamentally.
Okay, why? Is it just that shining a bright light bumps the electron too much? Is the electron too delicate?
That's the explanation Feynman gives, based on what we know. Light itself isn't continuous. It comes in lumps, 2 photons. To see the electron, at least 1 photon has to bounce off it.
Right.
And that photon, even just one, carries momentum. It gives the electron a significant jolt, a kick. And that kick is apparently just enough to change the electron's path randomly, smearing out that very precise interference pattern.
Okay, so maybe we can be clever. What if we use really dim light? Fewer photons.
Good thought, but it doesn't solve the problem. Dimmer light means fewer photons, so we just see fewer electrons. But the electrons we do see still got kicked by a whole photon with the same size jolt. The pattern for the ones we see is still the classical sum.
All right. What about gentler light, like lower energy photons, using longer wavelengths, red light, or even radio waves? They have less momentum, right?
That's lambda.
Less kick.
Exactly. Longer wavelength means less momentum, less disturbance. So we try that. We use light with a very long wavelength.
Does the interference come back?
Yes. As the wavelength gets longer and the jolt gets smaller, the interference wiggles start to reappear.
Success. So we can see the path and keep the interference.
But here's the inescapable trade-off. As the wavelength gets longer, what happens to our ability to see where the flash came from?
Oh, right. Long wavelength means low resolution, like trying to see detail with fuzzy vision.
Exactly. The flash becomes so spread out, so fuzzy, that we can no longer tell if it happened near hole 1 or hole 2.
So, just when we reduce the disturbance enough to get the interference back.
We lose the very information we were trying to get which hole it went through. The only way to have the full interference pattern is to have no possibility at all of knowing the path.
Wow. Nature enforces this. You can't have both.
It seems fundamentally impossible. And this leads directly to one of the pillars of quantum mechanics.
Heisenberg's uncertainty principle.
That's the one. It's not just about our current technology being clumsy. It states that it is impossible, even in principle, to design any apparatus that can determine which hole the electron went through without disturbing the electron enough to destroy the interference pattern. It's a fundamental limit baked into reality.
So this whole watching experiment forces us into a really weird logical corner.
A very tight corner. A logical tightrope, as Feynman calls it. Here's the conclusion we're forced into. If you set up your experiment specifically to find out which hole the electron passes through,
Like with the light source on?
then the results are consistent with the electron having gone through hole 1 or hole 2. Proposition A holds.
Okay.
If your experiment is not designed to determine the path, if the light is off, or the wavelength's too long to tell,
Then you cannot say the electron went through hole 1 or hole 2, even though it arrived as a lump.
correct. If you assume it must have gone through one or the other, even when you weren't looking, you'll calculate the wrong pattern. You'll predict the simple sum, but you'll observe interference. That classical logic simply fails when unobserved.
That's a huge shift for physics, isn't it? Giving up on knowing what actually happens.
It's a profound change, a retrenchment, Feynman says. Physics used to aim to predict exactly what would happen in any given situation. Now, for quantum events, it seems we can only predict the probability of various outcomes. The odds.
Like rolling dice, but maybe even weirder because the odds themselves change depending on whether you look.
Exactly. And nobody has found any hidden machinery behind the law, some deeper mechanism that explains why it's probabilistic or how the interference works when unobserved. It just is.
So can we quickly summarize the core rules of quantum mechanics that this one experiment reveals?
Absolutely. There are basically 3 fundamental points here. First, the probability, P, of any event happening is calculated from a complex number called the probability amplitude, F. Specifically, P equals the absolute square of F, PP equals F22.
Okay. Probability comes from squaring an amplitude.
Second, if an event can happen in multiple ways that are crucially indistinguishable or unobserved, like the electron going through hole 1 or hole 2 without the light on,
Mind what?
then you add the amplitudes for each wave first before squaring. So 5FU equals F1 plus F22, and the probability is PP equals F1 plus F22. This is where interference comes from.
Amplitudes add for unobserved alternatives.
Got it.
And the third.
Third, if the experiment is set up to determine which alternative happened if you turn the light on and observe the path.
Then the interference vanishes.
Right. In this case, the interference is lost, and you calculate the total probability by simply adding the individual probabilities for each path. PT equals P1 plus P22, or pi P all equals F2 and 2 P all equals F22, and probabilities add for observed alternatives. So the rules change based on whether we're looking. That's the essence of it. It's bizarre, but it works. It predicts everything we see in the quantum realm.
One last question then. If electrons do this, why don't we see this quantum weirdness with everyday objects? Why did the bullets just add up simply? Don't bullets technically have waves too?
They do. According to the theory, everything has a wave nature, even a bullet, even a bowling ball.
So why no interference pattern for bullets through two slits?
Because the wavelength associated with a macroscopic object like a bullet is incredibly, unimaginably tiny. Remember, wavelength is related to momentum. Bullets have substantial momentum, so their wavelength is minuscule.
Okay, tiny wavelengths. So what?
So the interference pattern, the maxima and minima, would be spaced so incredibly close together, far finer than any detector we could possibly build, finer even than the atoms in the detector.
So any real-world detector like our backstop is just too coarse. It averages over billions of those tiny wiggles.
Exactly. It smooths everything out, averaging over those microscopic peaks and troughs. And what you end up measuring is just the smooth, classical curve, the simple sum of probabilities P dollars plus P22. The quantum effects are washed out by the sheer scale difference.
So quantum mechanics is always there underneath, but we only notice it for things small enough and isolated enough for the wave nature to manifest visibly.
That's the picture. The quantum world is defined by this particle-wave duality, arriving in lumps, but distributing according to wave interference rules.
And crucially, the impossibility of knowing the path without destroying that interference, a limit enforced by the uncertainty principle.
You've got it. That's the core message from this experiment.
So the final thought maybe to leave everyone with, it's not really about figuring out how the electron magically goes through both slits at once. That might be the wrong question.
Right.
The real mystery is why nature is set up such that asking which slit did it go through is fundamentally meaningless. It leads you to wrong predictions unless you actually perform the measurement to find out.
The question itself changes the reality it's trying to probe. It forces us to rethink what exists or happens when we're not looking.
A complete twist on our classical logic, all built on probabilities and amplitudes.
It really is.
Well, this has been fascinating, if a bit mind-bending. We hope you keep wrestling with these ideas about complexity and how nature really works at its deepest level. Thank you for joining us on this deep dive.